Она работает, я проверил.
So, dear colleagues, we are starting our last day of the school, and we will start today with the lecture given by Andrei Shiryaev, the expert in the characterization of nuclear materials. So, please, Andrei, start.
Yeah, thank you for the introduction. The word expert is not always applicable. I don't like it very much, but we are working a lot with real materials from nuclear accidents like Chernobyl. And so to some extent, I will I will tell you today about main features of materials which were either produced in experiments reproducing severe nuclear accidents, or which were really produced during severe nuclear accidents like Chernobyl explosion. So just a very brief reminder, which is relevant for this presentation, is I have to say something about fuel pellets. Of course, you are well familiar probably with this issue, but nevertheless, nowadays the nuclear fuel is usually sintered uranium dioxide or uranium. Sometimes it is done with mixture with plutonium dioxide is also used, so-called MOX fuel, mixed oxide fuel. And normally uranium enrichment of uranium fuel in uranium-235 is approximately 4% now. No, between 2 and 4%. Of course, you know that the fuel pellets are encased in hermetically sealed tubes, which are made from so-called zircaloy or zirconium-based alloys. Usually, these are zirconium with a mixture of niobium, something like 1 or 2% of niobium. Eventually, especially in the Western countries, with some other elements like chromium and so on. In Soviet Union, usually zirconium niobium alloys are used. And several rods are assembled in the fuel bundles. So here you see as a scheme of a fuel bundle from RBMK reactor. RBMK reactor is a Chernobyl type reactor, which are very powerful, and they are still operating in the former Soviet Union. And for why they are relevant for today's presentation is just because, for example, Chernobyl nuclear power plant was operating RBMK type reactors. So we have a fairly large fuel bundle, which is more than 7 meters long. So you have fuel pellets which are encased in the fuel rods, and then they are assembled into several bundles. And if you look in perpendicular direction, you will see that fuel rods are separated by so-called spacer grid. Spacer grids are usually made from steel or also from zircaloy. Of course, fuel bundles can have a very different shapes. And you see here fuel bundles made for different VVR reactors, for RBMK and so on. And just to understand, to get some feeling of the numbers of amount of the fuel, for example, in a large modern reactor, is you can have up to 1,700 fuel bundles in a large RBMK type reactor. And in total, it results in approximately 200 tons of uranium as metal in the core. When we speak about nuclear fuel, take an average pellet, uranium dioxide pellet. Initially, it has some residual porosity. It is, of course, highly compacted ceramics, which with density approaching theoretical density, and density is approximately 99% of theoretical density. But of course, you have some porosity. As soon as the pellet goes into the reactor, due to neutron irradiation, you have a lot of, you generate fission products. Some of them are gaseous products, like gases like xenon, for example. You have different elements which can be dissolved in uranium lattice or cannot be dissolved, and they form precipitates of so-called epsilon phase. But what is important here is that in nuclear pellet, in the fuel pellet, you have a very large thermal gradients. Uranium dioxide is known for very poor thermal conductivity. So the temperature gradient between the center of the pellet, where in the center the temperature can reach 2000 degrees Celsius or even higher, and on the periphery the temperature should be more or less equal to the temperature of the cooling media, something like 300 degrees. So you have thermal gradients of approximately 600-700 centigrades per millimeter. These are huge values, actually. Not so many other technological applications operate with such huge gradients. Well, so when the fuel goes into the reactor starts to operate. Initially you have some cracking, which may be pronounced or not so well pronounced. You have cracking both due to thermomechanical properties of the fuel and due to, as we already discussed, due to accumulation of different fission products. And in the end, you end up with so-called high burn-up structure. So the grain size of uranium fuel changed dramatically. You have very strong gradient in fission products like, for example, plutonium, fission and activation products like plutonium, which is very heterogeneously distributed along the pellet. But nevertheless, what is important that the fuel structure changes a lot during the operation. So let's go now to some of typical reactors like RBMK type reactor. So this is a large building. You have an actual reactor core, which is in the center, in the heart of the reactor building. Nowadays, the absolute majority of operating reactors contain the core, which is encased into confinement. It is one can say that it is a large steel can. So in the reactor core, you have, for example, graphite cladding. Graphite cladding was very typical in the early ages of nuclear era, and it is still used in some high-power reactors like RBMK, for example. And here, in this graphite cladding, you have a special radial holes into which fuel pellets are placed. So let's speak now about nuclear accidents. Unfortunately, civilian nuclear power is, if you speak in realistic terms, every reactor is a very complex engineering device, let's say. And due to some miscalculations during the design stage or human errors, some accidents may occur. And actually here you see a list of some serious nuclear accidents. You see that these accidents can happen basically in any country, in the United States, in France, in Russia, or in Soviet Union, in England, and so on and so on. And unfortunately, it is highly likely that some accidents will happen in the future. And Fukushima example is a good one. Good in the sense that it is a good example of the statement that the accidents will happen. So let's speak about some of the accidents, some of the well-known accidents. The first one was in 1952 in Canada, Chalk River reactor, when the whole reactor core was melted. But this reactor was relatively rapidly, let's say, immobilized. So it was completely covered with soil, and nothing reminds nowadays about this accident. First, very serious accident, which was important from environmental point of view, was an accident at Windscale nuclear power plant in the United Kingdom in 1957. It was also a graphite-based reactor, and here you can see actually fuel rods, and this is an engineer which is operator which is holding fuel bundle. So this is a lead protection, but nevertheless, you can understand that radiation levels are quite high. But at those days, people were working let's say, more reasonably and were operating even irradiated fuel with, let's say, minimal protection, which is completely unacceptable nowadays. So at Windscale in 1957, there was a severe fire of graphite cladding. And for 3 days, the fire in the reactor core was taking more and more fuel channels. Finally, the reactor was shut down, and despite the accident has happened in 1957, the final decommissioning of the reactor is scheduled for 2035, not earlier. So basically, nobody knows how much of fuel is still in the reactor core. You can find estimates between 11 and 15 tons of uranium, which is still residing in the graphite cladding, and not much is being done to solve this problem somehow. Very important, very important accident with quite serious consequences was a small reactor SL1 in the United States in 1961. This is a former reactor core, and actually it was a so-called reactivity-induced accident. We will speak about them later. And just to understand what has happened, that one of the operators, he started to raise manually. It was a technologically acceptable operation. He started to raise one of the control rod manually. Then there was a surge in reactivity and the reactor power, and this poor guy was simply pinned to the ceiling of the building by the flying control rod, because the power of the reactor increased dramatically. So it was, this control rod was simply expelled like a bullet. So very large accident, for example, at the 3 Mile Island accident in the United States in 1978. So fortunately, this reactor the core was in the steel confinement. So not much has happened with the environment, because radioactivity release to the environment was very minor. But nevertheless, what has happened, that due to some mistakes of an operator and some very poorly designed scheme of announcements for the operating staff, so they simply didn't understood what was actual position of some cooling valves and so on. The notations were not really clear. So the reactor started to be, the coolant went off. So this temperature of the reactor core started to increase dramatically, which led to complete melting of the significant fraction of the core, with formation of the melt pool. And finally, this melt pool, which was kind of hanging in the middle of the reactor core, it penetrated the crust which has formed, and started to pour down into the lower premises of the confinement vessel. And one can estimate that approximately 200 to 300 kilograms of very hot uranium zirconium oxide in a molten state were going down every second for something like 5 minutes. Okay, these are just some main accidents which has happened, let's say, in the West. And here we will speak about Chernobyl. This is a photograph of a Chernobyl power station soon after beginning of the operation. You see 2 very large blocks, and actually the length of this building is something like half a kilometer, 500 meters. So after the accident, which has happened on in the night of 26th of April in 1986, there was a very large explosion. You see famous, here you see famous photographs made from helicopters. So you see that the reactor core is completely destroyed. And what has actually happened, that if you look at the scheme of the so-called shelter, this is soon after the accident, so-called a shelter was created to confine reactive debris inside it, to prevent even larger contamination of the environment. So the reactor core was actually here. So the reactor core you saw in one of the previous slides, it's a big cylinder with something like 190 tons of uranium dioxide as a fuel. Now it is completely empty. With the red color, you see some so-called Chernobyl lava, and we will speak about them later. So, and all the rest, just parts of the reactor building. Actually, you can see that these numbers are in meters. So you can see that the building is quite large. And just to understand the scale of the accident, so this is called the upper biological shield. This is the upper biological shield, which was thrown up during the accident, during the explosion. And then fall back. The diameter of this construction is 14 meters. So you see humans, people are standing here during the mounting of this upper biological shield in one of the RBMK type reactors. So the thickness is approximately 2.5 meters. And of course, this biological shield was connected initially with the reactor core by a huge number of tubes. And all this was ruptured, and this very large cylinder filled with serpentinite and with iron shard was thrown up. So the explosion was quite dramatic. So why do we need to study materials which are produced during nuclear accidents? First, we can get some understanding about how the accident really progressed during the event. And this is important for development of measures to prevent such accidents. Second important thing is we can try to develop new materials which are more resistant against the accidents. For example, accident-tolerant fuel or sacrificial materials, and we will speak about them later. And of course, we can develop optimal procedures for dismantling of damaged facilities. So there are two main types of reactor accidents, so-called LOCA, loss of coolant accidents, and RIA, reactivity-induced ones. So LOCA, which are, let's say, much more common, and they are, in many senses, are easier to reproduce. They happen on a time scale of minutes or tenths of minutes. Here you see an experimental set of fuel bundles which were subjected to experimental LOCA type accident. You see fuel bundles which are severely melted in the middle. So what happens? You are losing coolant. Still, the reactor is operating, so there is a huge release of heat, and you don't have cooling. So eventually, materials which are inside the reactor, inside the core, start to melt, forming corium and the materials which we will speak about. The reactivity-induced accidents, they happen when for number of reasons, and actually the number of reasons is one can speak about many possible configurations of the reactor core when very rapidly the reactor power can increase dramatically. Usually these are kind of very short pulses lasting for several milliseconds. And of course, nowadays they are more or less avoided, but especially in the early ages of the nuclear power industry, they were relatively common. So when you have a relatively small increase in the reactor power, the fuel rods, they basically remain the same. As soon as you start to increase the amount of energy which is introduced into the fuel during the surge in reactor power, finally your zircaloid tubes, they can start to swell, crack, and eventually fragment. And actually, if you think about these events, you have a very hot fuel which is inside metal rod or zircaloy rod, and it is still and the rod is surrounded by coolant. Coolant is for example, liquid, some supercritical water or liquid sodium or something else, and you have a very rapid reaction between very small particles of very hot uranium fuel. For example, the temperature of, here, very hot means something like 2000 degrees centigrade or even higher. Fuel can be even melted during reactivity-induced accidents. And these very small pieces of fuel start to react with a coolant. Of course, we have a steam explosion. If you start to model fuel cladding interaction, you can model it in many ways. Of course, you need high temperatures. You can play a lot with the atmosphere. You can make in inert atmosphere, in steam, or in oxygen. But what are important features is that zirconium or zircaloy melts approximately at 1800 centigrades. It is relatively high temperature. But if you have a contact of zircaloy with steel, for example, with spacer grid and so on, you can form eutectics, and the temperature of the eutectics between steel and zirconium has a temperature of melting temperature of approximately 1300 C. What is important is that molten zircaloy very readily liquefies uranium fuel and zirconia or zirconium oxide. So interaction of molten zircaloy with fuel, uranium dioxide has a melting temperature of 2800 degrees, even higher. So to melt the fuel, it is not so easy. But if you have a molten zircaloy which starts to interact with zirconia, fuel starts to liquefy. So it is kind of a melt, not proper melt in physics from the physics point of view, but actually its behavior is like a liquid. What is also important is that zirconium metal is one of the most efficient getter of oxygen. So it consumes oxygen and you start to oxidize zirconium from pure metal to first to solid solution of oxygen in metal and then to zirconia. But what is important is that the gettering properties of zirconium are so high, so you can even reduce uranium dioxide towards metallic uranium. But what is interesting that you can have a very strange and unusual interactions. For example, this is a cross section of experimentally destroyed molten uranium dioxide fuel embedded into zircaloy tube. So this is part of a fuel pellet. This was a former zircaloy. You see very strange interactions between these materials, and on the micron scale in the fuel you have a very strange interaction. So here you have some fuel which was liquefied, and here you have zirconium which is partly oxidized to zirconium dioxide with a lot of very strange and complex interactions. When you the absolute majority of the experiments on fuel cladding interaction concentrate, of course, on non-irradiated materials because they are much easier to work with. Nevertheless, there were some experiments which try to reproduce what is going on with when you start to melt irradiated uranium dioxide fuel or MOX fuel. So here you see photographs made from in the hot cells, so that's why this yellowish appearance. You have irradiated and non-irradiated uranium dioxide fuel and MOX fuel. And you see that non-irradiated fuel, so again, you have a fuel pellet surrounded by cladding. So non-irradiated fuel, depending on the duration of the experiment, so ranging from 1 second to 10 minutes, you see that non-irradiated fuel is behaving more or less regularly. Irradiated one reacts more readily. So you have a very strong interaction between zircaloy, between fuel, with formation of zirconia and so on. MOX fuel behaves completely differently. And if you look at the cross sections of these materials. So you have a very large difference between, for example, non-irradiated uranium dioxide fuel and irradiated ones. Why some images are missing here is that simply because irradiated and non-irradiated MOX fuel, which were interacting for at 2000 degrees for several minutes, they were simply physically decomposed, fragmented. So you don't have a solid sample anymore. You have a very strong reaction. So the cladding and the fuel pellet are completely fragmented and just forming some debris. And of course, you see that the shape is changing a lot. So in the center part, you have some remnants of the fuel. In the periphery, you have some remnants of the cladding, which is usually converted to zirconium dioxide with considerable fraction of uranium, for example. What is going on during the locotype accidents in a general sense? First, you start to dry the reactor core, and you may have very important steam generation. Of course, when you generate a lot of steam in a closed confinement, you can have a very strong pressure rise. And this is very bad of course, from engineering point of view. So when people design the confinement, the confinement should keep quite a considerable overpressure from the inside. And initially, the fuel rods start to heat at approximately 1 degree per second, so it is relatively slow. Something like at 800 degrees, zircaloy starts to swell. And actually, peculiarities of this process are depending on a lot of parameters. So the swelling can be very anisotropic, but this is the issue which is studied quite a lot in zirconium engineering. And sooner or later, the cladding starts to break. You observe cladding rupture. What is important that at 1230 degrees, so-called steam zirconium reaction starts. Zircaloy starts to be oxidized by steam with huge release of temperature, of heat and hydrogen. So at this stage, this reaction is strongly exothermic and it is self-supporting. So that the core starts to be heated at a rate of approximately 10 degrees per second. So to go from relatively modest temperature of 1200 degrees to a temperature which is completely unacceptable from engineering point of view of something like 2000 degrees, you have only several minutes. Several minutes is so very often one can see the statement that zirconium oxidation by steam is very fast. Fast is very subjective thing. Fast from the physics point of view or chemistry point of view or kinetics is not very fast. But if you are an operator of a reactor which is unstable, you have only maybe 2 minutes to understand what's going on to make some critically important decisions. 2 minutes is not much. But from the physics point of view or from kinetics point of view, the zirconium steam interaction is not that fast. Finally, you form a melt of liquefied fuel, liquefied zirconia with temperature up to 2000 degrees or even more. And this so-called corium starts to relocate. So it just forms drops and falls down into lower premises of the confinement. If you have some water, there can be some reaction with water, with explosions and so on and so on. So locotype experiments. These are optical photograph and X-ray radiography of fuel bundles. You see that, for example, in the center part of a bundle which underwent locotype accident, you have simply a void. So all the fuel bundles, they were molten fuel bundles forming corium. They simply drop down to the lower premises. Of course, integrity is there is no guarantee that the integrity of the whole fuel bundle will be preserved. Actually, here you can see cross section of one of these experiments. So fuel pellets. It is just a cross section in this direction, similar to those ones, and you see fuel pellets and these small things are just ruptured zirconium claddings. So damage to the fuel bundles is severe. Let's go now to an actual example of Chernobyl accident. Chernobyl accident was not a locotype, so the coolant was still there until before the explosion. But what is important that in Chernobyl, in reactivity type accident, you can see that the neutron power was increasing dramatically. So there was some experiments, so you see time scale in seconds. There were a lot of instabilities before, but what is remarkable here is that the neutron power was relatively constant for during up to several seconds before the actual explosion. Then the neutron power started to increase. And the increase was so severe that it led to extensive heat generation and finally the destruction of the core. Of course, there were a lot of previous events not fully understood, but what concerns the neutron power was going up very rapidly. This is a typical reactivity-induced accident. And the temperature of the reactor, which was relatively stable at around 200 degrees for the coolant, it started to increase again dramatically during the accident. So what has happened during the Chernobyl accident from the materials point of view? Prior to the explosion, you have some instabilities which are leading to formation of zirconium, uranium oxide systems. And I will show you some of the hot particles which were formed during this period of the accident. Then you have a reactor destruction. In Chernobyl case, it was just an accident, just an explosion. You produce so-called hot particles. Subsequently, formation of so-called Chernobyl lava or lava-like fuel-containing materials has happened, and lava started to interact with concrete. We will discuss it quite a lot. No, and currently there is some generation of aerosols from radioactive aerosols from the lava. Hot particles. Here you see a typical fuel particle which was expelled from the reactor. These are SEM images. You see some bubbles which were formed by fission gases, gaseous fission products. No, but basically this particle is just a normal fuel which is after several months or years of the operation. You see a very typical morphology of the fuel. At the very same time, you can find hot particles with a very complex structure. So you see a particle which is something like 150 microns in size, and you have zirconium rich, uranium rich, and intermediate zone. So here there was a fuel, here you see cladding, remnants of the former cladding, and you have an interaction layer. So prior to the explosion and in the moment of rapid temperature rise, fuel started to interact with the cladding, forming these very complex materials. And if you look at the microstructure, again, these are SEM images. You can have a very funny, and from material science point of view, funny structures which indicates that there was strong, there was a high temperature interaction of uranium and zirconium in this oxidized particle with partial decomposition of solid solution and so on and so on. And you can trace behavior of different elements. For example, here in zirconium-based particle, you have some precipitation of uranium, which is excess uranium, which was not able to dissolve in zirconium dioxide. But here you see, for example, an amazingly complex one, hot particle from Chernobyl. The brighter is, the heavier is the material, so it's more uranium rich. So in the center, you see the whole, the particle itself, and here you see some interesting pieces of some regions of interest from this particle. And you see some features of thermomechanical flow. So some material was plastic at high temperature, it was plastically deformed. You see features which are indicating of very rapid cooling or quenching of the material which was expelled from the reactor with formation of crystallographically oriented lamella of decomposed solid solution. You have numerous white dots. White dots are just uranium dioxide, which was expelled from the matrix. For example, here from the zirconium dioxide matrix, because during the reaction, at high temperatures, solubility, of course, of uranium in hot zirconia is very high. When you cool down, some of the excess uranium dioxide is expelled and segregates. So another interesting type of materials can be found in so-called under reactor room 305. This is a reactor core. The reactor core was completely destroyed, and we are speaking now about this room. This is actually during the operation of the reactor. This room is kind of an extremely hot radioactive sauna, because all the feeding water is coming in the pipes from through this room, and the temperature during normal operation temperature in this room is approximately 150 degrees. And it is forbidden to enter there because of very high radioactivity. But after the accident, this room was the place where most events has happened. So because the materials from the reactor was simply thrown into this room. You can see optical photographs made by Konstantin Checherov soon after, several years after the explosion. Actually, when you think about radioactivity level, 5 years after the accident, there was more than 20 Roentgens per hour. So in this room, so the activity level was very high, and people just entered for a few minutes, made some photographs, and just rushed away. So you can find very strange materials. So this is a piece actually of water, of cooling a tube, of metal tube, with some slug, which is molten to this tube. And if you look with electron microscopy at this slug, you see that these are basically iron oxides plus some chromium and nickel. This is basically just molten steel, but with a lot of very funny white precipitates. And white precipitates is a molten uranium oxides. As you know, pure uranium, stoichiometric uranium dioxide melts at very high temperatures. Very high temperatures here means 2,800 degrees, and such temperatures are unlikely to be achieved at a large scale. But if you have hyperstoichiometric uranium dioxide, for example, uranium 308, the melting temperature drops quite considerably. So when the stoichiometric fuel starts to interact, hot stoichiometric fuel starts to interact with hot steam, it starts to oxidize, forming hyperstoichiometric uranium dioxide, and it melts easier. Of course, you also have some contribution of zirconium, which also liquefies the fuel. And so you have you can observe here very interesting, from materials point of view, very interesting features of molten uranium hyperstoichiometric uranium dioxide. And you can have a very rich variety of different structures, which are showing different stages of the accident. You can also find so-called 5-metal particles. 5-metal particles are fission products like technetium, palladium, ruthenium, rhodium, and some other, which are not soluble in the lattice of uranium dioxide fuel, and they're expelled from the crystalline lattice of uranium dioxide and form small means nanometer, micron size small particles, which are now very important for treatment of highly radiated fuel. And these small particles contain, for example, platinum group elements and so on. So what's going on when these molten corium, or again, corium is a melt of uranium dioxide and zirconium dioxide. What happens when this molten corium starts to interact with concrete? So the reactor is destroyed. You have formed these very hot actually, of course, very radioactive material, which starts to interact with concrete. You see some examples of experimental studies. So people make artificial corium and then spill it to specially designed concrete floor. You can have you can trace how does this melt spreads along the different types of concrete and so on and so on. And nowadays, in modern reactors, so-called sacrificial materials are used. So under the confinement, you have a special room, which is the walls of this room are made from so-called sacrificial concrete, and you have special trap of the melt. And if the reactor is completely destroyed, which is a very unlikely scenario, the corium should go to this corium trap, and the material from which the walls are made are especially designed to consume a lot of heat from when the reaction between the molten corium and the concrete happens. So the corium should be solidified here, and then you can try to somehow to dismantle the reactor building. Oh, sorry. But what is going on if you don't have this corium trap? And actually, corium traps started to be designed only relatively recently, somewhere in 90s. But what's going on, for example, in Chernobyl case, if you look at the power of the reactor, which is shut down, and immediately after the shutdown, the heat generation is approximately 6.5% of the power of the reactor prior to the interruption. That's why you can, prior to shut down, to scram, for example. So even if you stop the reactor right now by pushing a scram button, for example, still a lot of heat generation will occur. And of course, this heat generation due to short-living isotopes decreases rapidly, but nevertheless, it's quite considerable in real terms. So if you have debris of the reactor core and you put something on top of it, for example, construction materials, you start to melt. Yeah, and then you produce so-called MCCI, molten corium concrete interaction materials, which are looking like kind of a glassy or ceramic material. You have some, you see some images from the experiments. These are graphite capsules. You have some reddish or brownish or gray glass or ceramic, which was formed during the interaction between uranium dioxide, zirconium dioxide, and sand or concrete. And in Chernobyl case, for example, and most likely in Fukushima, this interaction led to formation of large amounts of thousands of tons of so-called Chernobyl lava, which looks like black or brown material, glassy material with very high levels of radioactivity. For example, this is a photograph of a famous elephant foot, which is well known after this stupid movie Chernobyl. Actually, this is very small flow. It is just the very end of one of the flows. It is just very well, marketing is doing it very important thing, but it is very small actually. When the lava goes into water, it starts to form so-called pumice. And here, for example, you see photographs of steam discharge corridor in the reactor building, and you have some flows of frozen lava. So the lavas were forming in the Chernobyl case. They were forming in the under reactor building. You have some schemes of different lava flows. And if you look at actual images of this material, this is a piece of brown lava in epoxy resin. You can see inclusions. You can see a lot of, I don't know if it will, this is X-ray tomography. You can see a lot of inclusions in it. And if you look at these inclusions, you find a lot of interesting phases. First, you can find some pieces of remnants of the fuel, uranium dioxide. Again, these are not exactly stoichiometric uranium dioxide. It is mostly hyperstoichiometric uranium dioxide with a mixture of zirconium. You see molten drops of droplets of molten steel. So droplets of molten steel indicates that the temperature of this melt was definitely higher than 1500 C and for quite a prolonged period of times. And you have different parts of different variations of zirconia-based materials and zircon or zirconium silicate, which was formed when zirconium dioxide started to interact with surrounding metal melt. Here, for example, you see uranium dioxide fuel, which was molten and forming a hyperstoichiometric fuel. Most likely, this is just a partly molten uranium dioxide pellet. And from optical spectroscopy, you can make a lot of conclusions about high concentration of uranium inside. You can look at, for example, transmission electron microscopy. You can find very interesting peculiarities, for example, for inclusions of different phases inside. And why it is important, it tells us about the progression of the accident, how this melt was evolving this time. You have these zirconium-based, zirconia-based phases, which are partly crystalline. But what is important is that zirconia is normally at room temperature is usually monoclinic. At high temperatures, especially during the accident, it was tetragonal or even cubic, indicating very high temperatures. But what is important, if you look at these zirconia-based particles and you just slightly press it mechanically, they start to decompose, to fragment. And if you look at these inclusions inside the lava, you can see very often, you can see cracks around it. And why these cracks are forming? The cracks are forming because initially you can have so-called partly stabilized zirconia, which is tetragonal or cubic. And upon interaction with surrounding moisture, for example, it starts to convert spontaneously into monoclinic variety, and monoclinic variety is has much lower density. You have a large volume effect. Then the matrix, the glass in this case, matrix can start to break. So you can make some conclusions about when different particles were formed at the early stages of the accident, at the later stages of the accident. And all this information we can get from investigation of materials in the reactor. For example, this is a fuel bundle, this is a scheme of the core, the neutron profile in the beginning of the accident. When the accident has started, the neutron power was peaked in the lower part of the core and the material started to melt. Nuclear graphite, we're closing to the end. It is already a different type of the material. These are images from wind scale. You see some remnants of the fuel pellet. And you see here destroyed, formerly it was metallic uranium fuel. At wind scale, there was uranium metal was used as a fuel. After the fire, you have some mixture of strange material, and the British, they were very much aware that uranium hydride, which is pyrophoric, which can burn spontaneously, was formed. But fortunately, uranium hydride is not very important. These are mostly just uranium dioxide. And for example, one of the Russian reactors of RBMK type, which was repeatedly operating during in very difficult conditions with some accidents. And during these accidents, the fuel bundles were destroyed, and the material, the irradiated fuel, was dispersed into the cladding, forming so-called hotspots. For example, this is a neutron scanning of the whole reactor core. You see that some channels, this is something like 9 meters, so you see a very large contaminated area. And if you look at this graphite, you want to develop means to decontaminate these reactor cladding. You look with, for example, scanning electron microscopy. You know that the activity of this material is very high, but you cannot find actual fuel. You look with scanning electron microscopy, you see a lot of very strange phases, but they are not containing uranium at all. Still, you have a very high radioactivity. And finally, we were able to locate, for example, highly radioactive particles. So this is a piece of graphite covered with some silicates. Silicates are coming from river water, which was used to cool the core after the accident. And some of them, they contain plutonium, uranium, and other radionuclides. And these, for example, are very small particles, so they are micron size or even less. They are highly contaminated with radionuclides, but you cannot have you cannot find really chunks of, for example, uranium fuel. You have very tiny particles of former fuel, which are spread over the whole the whole graphite cladding. And why it is important is that when you try to decontaminate this graphite, you take graphite, you start to clean it with different solutions, and nothing happens. Then suddenly you have a very large release of radionuclides. Why it happens? It happens because radionuclides are confined to small, for example, silicate particles. And first you have to dissolve these silicate particles. And as soon as you dissolve them, you observe release of radionuclides. So it is a very strange thing, but it is very relevant for many old reactors which underwent reactor accidents. Okay, I think that I'm already has spoken too much. If you have some questions, please.
Thank you.
Everybody starts during the last day.
Just one question. For this analysis of the Chernobyl lava or other examples, this equipment, is it some specialized equipment with the shielding from the radiation, some special detectors? I don't know.
Of course, you should ideally use nuclearized devices first to protect yourself, second to minimize damage to the detector, but also you can try to minimize the size of the sample, and then you can partly avoid all these problems. But of course, usually people work with nuclearized equipment.
Thank you. Any more questions? If not, then let's thank the speaker again. So now I will check our second lecture. Yulia, you are here.
Hello, Vladimir.
Just a moment, I will. Yeah, so now you can share the your presentation.
Yeah.
Now you can do it probably. Yeah.
Okay. Now you can see full screen, right?
Yes. Yes. Perfect.
Okay, perfect. So from really difficult and complicated topic to let's move to, I think, more relaxed one, let's say, but still really important also for decommissioning projects. So it will also recap a little bit on my yesterday's presentation that was featuring the safety documents of IAEA, and so you will see some resemblance. Something will definitely look familiar, and I will refer to some of these things that I was telling yesterday. So today's topic is decommissioning planning and related documentation, and mostly I will speak about the decommissioning plan itself, but I will also touch upon in this presentation on other documents that come in package for that or provided along with that. To begin with, let's just start with some objectives of decommissioning again. So as I was mentioning, objective of decommissioning is to remove facility site from regulatory control, to remove the hazards existing at the radiation facility or nuclear facility. And that has a number of features, such as this process includes both administrative and technical aspects that needs to be considered, treated, managed, both on the level of planning and on the level of stage of implementation. And the decommissioning process and procedures do differ from ones that were happening to facility and also to staff that work at the facility in the operational phase. And that definitely should also be borne in mind. Because, for example, if a facility was in operation for 20, 30, 40 years, and it was kind of this repeated actions, certain actions that are familiar to staff, that are covered by necessary procedures, safety system, quality system, etc. Then when we come to the phase of decommissioning, it's absolutely to some extent it's similar, but many of the processes, many of the actions are really different from or unique or happen only once in a lifetime of facility. And that requires also change of mindset for the personnel, special training, change of even organizational structure or creation of organizational structure for the decommissioning project, and many other aspects to be considered, including radiation protection aspects for this phase, and industrial protection, and all other things involved. This, of course, implies that we should have all necessary planning documents, supporting documents in ready phase, and this should include all necessary substantiation of the actions that we plan to take during the decommissioning phase, and we need to prove to regulator that it's all considered in scenarios and it's going to be implemented in a safe way as well as in an efficient way. So talking about that, safety is of course key importance, and it's a responsibility of the licensee to implement it all in a safe manner, and it's everywhere stated in IAEA documents that responsibility for safety always stays with the licensee, even in case that we invite licensee invites contractors to perform the decommissioning job or certain works within that process. Yes, and as I mentioned, when we come to the phase of decommissioning, we deal both with radiological and non-radiological hazards, which should be also considered in necessary safety assessments and in other decommissioning documents. Protection of workers, public and environment keeps being the priorities. So this should also cover these new hazards that might occur and planned to be occurring during the decommissioning phase. So this should also be addressed in the planning documents for decommissioning. And along the process of decommissioning, we deal with the generating of waste, such as from different operations like decontamination, like dismantling. And so this should be also covered in relevant planning and possibly minimized. So there is a hierarchy of waste that keeps being applicable both for operational phase and also for decommissioning phase. And when we talk about decommissioning, we normally use the term graded approach. as I was referring yesterday, that that means that the actions, planning, documents, scrutiny from regulator, and actions from and planning and implementation actions from the licensee, they should be commensurate with the present hazards or expected hazards, with the complexity of the facility itself and complexity of the actions and activities during the commissioning that need to be implemented to reach the end state and to get the decommission license terminated. So yeah, this is about graded approach. So when we talk about big and small nuclear and radiation facilities, of course they are of different, many different types, different hazards. Kind of applicable to them or connected to them. Level of complexity of the facilities are very different. So when we plan decommissioning, it can be very also imply different actions needed from just removal of the source to decommission of big facilities such as nuclear power plants or other complex things like facilities like big research reactors or nuclear fuel cycle facilities. Of course, they all have their own features that also are reflected in what level of detail should be in your decommissioning planning, all documentation, analysis done, etc., etc. So yes, as I mentioned, the level of details and efforts should commensurate with types and magnitude of hazards potentially expected, and also with potential consequences for workers, for public, and for environments from the actions that we take, and for potential, let's say, unplanned actions like these situations that might occur due to some certain hazards. It should all be addressed in the planning. And the graded approach is applied actually to all aspects of decommissioning as well as to all phases of the facility lifetime. And one of the important aspects of that or conditions is that all of these actions should not compromise safety of the facility and of the personnel and environment and public, and also it should be done in compliance with the relevant safety requirements and safety criteria. And efforts should be optimized. So by using graded approach, we also mean that it should be to a certain extent rational. So it shouldn't be become too burdensome for the small enterprise, for small facility to. So there is no sense to include more complicated actions when it's really not needed. So it should also reflect some common sense in that. Now coming to the decommissioning plan and major other documents, but we will concentrate on these documents. So decommissioning plan is a principal document that's for decommissioning, and it is prepared by the licensee, and it provides also the regulatory body with safety-related information on how the licensee plans the decommissioning process to be implemented, and how will he reach the organization reach the end state for the decommission. So this is actually the cornerstone of a successful decommissioning project. And the regulatory body is responsible to ensure that workers, public, and environments are well protected, enough protected during decommissioning activities. And regulator is required to ensure that facility operator has identified and has resolved the safety issues on the stage of planning. So it's all covered in relevant documents. This plan, decommissioning plan, also brings together all information on proposed decommissioning activities, identified relevant safety issues. So it should all be contained there. But the kind of level of detail of decommissioning plan. It's not like always the same. So it starts from initial plan that is very tentative and only has a big picture as we see it, and then along the coming to the phase of decommissioning, we get it updated and reaching the final decommissioning plan. Here I included the list of documents that normally can be prepared or can be required by regulator from the licensee to be accompanying decommissioning plan. So besides decommissioning plan, they can be these plans and reports that you see here in the screen. Can be just some of them, especially if we talk about smaller facilities. So some aspects sometimes are not required to be covered in some separate documents. And often for smaller facilities, for example, it can be the case that you only have a decommissioning plan and the licensee can just include some chapters, some sections into this plan where it's just covered shortly on these aspects. But basically the typical related documents include characterization plans, both for survey plan and then reports. Same as for final radiological survey and reports. The plan even for public relations, for involvement of interested parties, same as we call them stakeholders, but in IAEA terminology it's called interested parties. Also information on site policies, different programs and procedures applicable, and final commissioning reports is a final document that is provided at least at the level first what will be included and then the actual documents. Also, the documents that are prepared to accompany the decommissioning plan are historical site assessment that helps to bring together necessary information about the early phases and up to and including operational phase of the facility. And that helps us to see what can we expect due to the certain conditions of operation of facility or whatever was its track record of some minor incidents, villages, something else, modifications, so it's all included there. And the training plan for personnel, because as I mentioned, this is a new activity, so anyway, the personnel should be trained if they are to be involved in these decommissioning actions. Other supporting documents that can be included can be provided separately or can be a part of the decommissioning plan as chapters or sections. Includes the examples of them are transition plan for the transition phase. Transition phase normally happens still under the operational license, and it includes these preparatory actions and activities that operator does to prepare for decommissioning. And in the end of this phase, the final decommissioning plan should be prepared. Site preparation plan kind of accompanies that safety assessment. One of the really important documents to be prepared for and to accompany the decommissioning plan: environmental impact assessment, same environmental protection plan, waste management plan, cost estimates, and others, other documents that you can see here. Similarly, they can also be separate documents, or they can be incorporated into the decommissioning plan. A couple of words about requirements. Yesterday I was touching upon the GSR Part 6. This is General Safety Requirements Part 6 documents of IAEA called Decommissioning of Facilities. And the requirement number 10 in this document is planning for concerning planning for decommissioning. And it states that licensee shall prepare a decommissioning plan and shall maintain it through the lifetime of the facility in accordance with requirements of regulatory body in order that decommissioning can be accomplished safely, to meet the defined end state. So basically that describes what needs to be done. That it explains that licensee should start preparing the decommission plan in some early phases of facility lifetime life cycle, and then it is being updated in accordance with a necessity. There is some regular not duration, but regularity of this updates that is normally established by the regulatory body. Also, this is in GSR Part 6. Additionally, I mentioned here for small facilities, there is how it's implemented in ISSG-49, for example, in Section 7, planning for decommissioning. Also, of course, relevant similar lines are in ISSG-47 for larger facilities. So this requirement is further translated into the level of specific safety guides on the planning of decommissioning, and that is described how it should be prepared. Here you see a big scheme that shows how the decommissioning plan evolves during the different stages of facility lifetime. So initial decommissioning plan can be prepared as early as actually even before. This is just the scheme that I reproduced from the safety guides, yes, but and it says that initial decommissioning plan is done in this construction phase under the license for construction, but it can also be done even earlier in some design phase, in the planning, siting phases. So so somewhere early in the lifetime of the facility. So here at this phase, at this stage, it's very tentative, very preliminary. So of course we don't have any information about exact information about how facility would be going through the operational phase. So, but we already have some initial considerations to be put into this plan to facilitate future decommissioning process. And for example, like in these stages, early stages, we already have information about materials that are used for construction. So we can preliminarily assess how these materials would be potentially contaminated and activated due to their chemical composition, to their properties, to the shapes, geometry, and disposition in the facility, equipment that would be used, etc., etc. So some initial data can already be considered in this initial decommissioning plan. Then here, I don't know if it's clearly seen here, but also this shows what license covers the phases. So under which license the facilities operated in each of the phases. And so updated decommissioning plan has more, already incorporates some more details and more documentation is prepared. And final decommissioning plan is prepared, as I mentioned, in this normally in transition phase, in the phase of preparation for decommissioning. And at this stage, it already incorporates more details and more additional documents, such as safety assessment, environmental impact assessment, and some other documents. And somewhere here in the end of this phase, the final decommissioning plan is submitted to the regulator. It's after permanent shutdown. So FDP is prepared, it's submitted to regulator, also based on the characterization that is done that shows what kind of scope of works can we expect, what contamination is expected, what activation is expected, something like that. And if in positive scenario, the FDP is approved by the regulator, we can go ahead and proceed to obtaining, so based on that, the licensee obtains the decommissioning license or decommissioning authorization, and then the works are happening under this decommissioning license or authorization. the actual decommissioning works. And even that is not the end of the decommissioning planning. So it is still possible that the decommissioning plan might need to be updated based on when you really start to dismantle, to decontaminate, to dismantle the elements, system structures and components of the facility. Sometimes it contains some surprises. So, for example, when you start to actually drill and make more works, etc., dismantle something, and then sometimes licensee realizes that there are some other issues that were hidden from the eyes or hidden from the documents, and sometimes with materials, sometimes with some deeper activation somewhere in the structures where it wasn't expected, or something else. And some materials that are now not normally used, but they were used in some earlier times of nuclear programs worldwide. So even not only but radiological, but also like hazardous materials that can present some issues. So sometimes it requires additional work on new calculations, new analysis, update of the plan, so that to ensure and to confirm with the regulator that even in new conditions or with new circumstances, it will be done in a safe manner, maybe in a little bit different set of the activities and works to be done. And the final document here is final decommissioning report that is prepared based, I didn't include here, but based on the final decommissioning radiological survey. So this report is submitted to regulator after the finalization of decommissioning works, and then it's the task of regulator to check if the end state was reached, if works done, activities done on decommissioning really enabled the licensee to remove all plant hazards and to reach the end state in accordance with the decommissioning strategy that was chosen for this facility and put into the final decommissioning plan. So here just a little bit more explains about these iterations of the decommissioning plans, from starting from initial plan through updated plan. And by the way, there can be more than, of course, more than once can be updated. So, for example, as here it's mentioned every 5 years, but for different facilities it can be different cycles, lengths of cycles for revision. That also relates to other processes in the facility, so that it would be really like make sense and fitting other cycles. So coming to the final decommissioning plan, it's really much more detailed. It's prepared before decommissioning, and that serves the basis for authorization for decommissioning or license for decommissioning to be issued by the regulator. It also incorporates characterization survey information. So this is really important bunch of works to characterize the system structures, components, and the facility as whole. And as some of my colleagues often say, that you have 3 most important actions in decommissioning. That is characterization, and characterization. So even when we do not clearly focus here on that, but that's just to mention that this is kind of one of the most important inputs of information for the licensee to base on them all the further planning of the decommissioning actions needed. And as far as we have different options and scenarios for decommissioning, it can be immediate or deferred dismantling, how we call them. There is also the phased dismantling. There is still something that is not normally recommended or named in decommissioning strategy, but also there is internment scenario that still exists. So of course it should also be mentioned and covered. And sometimes that is the case that the operator, the licensee, just proves to regulator that this option is most viable. Yeah, but in case of for example, deferred dismantling. Also, the final decommissioning plan is updated, and some additional work is performed during this periods of safe enclosure that can be up to several decades. And the regulator then reviews, approves all changes into plan every time that licensee provides that, submits that. And to mention also that interested parties should have possibility and opportunity to review final decommissioning plan. And although it sometimes creates some concerns on behalf of licensees, that it can create some issues, but definitely it's strongly advisable to involve interested parties into this kind of discussions, because then it shows kind of responsible and sustainable approach of the licensee towards decommissioning, and also normally it's something that really interests the interested parties, communities, local communities, and other interested parties, especially when we talk about end state of decommissioning and release of sites, when we discuss whether it would be free restricted release or unrestricted release. So in case it's not unrestricted release, then of course the local community is interested, like what limitations will still be present, and also they are present because there are still some hazards present, right? So this should all be communicated in a good manner with the interested parties. So now coming to decommissioning plan contents, you can refer to this document ISSR-45, Safety Report Series 45, standard format and content for safety-related decommissioning documents. I really advise you to take a look at that, because it contains not only this information about what should be contained, but also it quite well describes and gives some explanations to the contents of this decommissioning documents to be prepared. So here you can see the typical content of the decommissioning plan. So it contains 15 chapters. There can be some additional ones, but typical ones are here. Introduction, facility description, decommissioning strategy. Or for earlier phases, for like when you prepare initial plan, normally both options of immediate and deferred dismantling are considered. And then in the final plan, one is chosen. Project management considerations, decommissioning activities, so actual works that are to be done during decommissioning, surveillance and maintenance necessary, waste management, cost estimations and funding mechanisms for the decommissioning project, safety assessment, environment assessment, health and safety aspects, quality assurance, emergency arrangements, physical protection and safeguards, and final decommissioning survey. Also, just I wanted to mention that in specific safety guide 49, decommissioning of small facilities, there is an appendix that's annex that contains also some contents of the decommissioning plan for small facilities. And further on, I talk about both of them. So for most of the facilities, we use this ISSR-45. But for smaller facilities, if it's the case for your organization, you can also take a look at this SSG-49 for the example of contents of a decommissioning plan. So now I will just briefly go through these chapters of the decommissioning plan to show you what normally is included there. So as for SRS-45, you can see that introduction contains some really basic information about the facility. Facility description is the next chapter, so it includes all the important information about the facility itself, including location maps, definition of project boundaries. That's very important. So, like in any decommission, like in any project activity, here we need to identify project boundaries. Otherwise, because otherwise it would potentially lead to some uncertainties or surprises, like about costs, about some activities that might be left uncovered, but still need to be done. So this is really important to make these boundaries. Buildings and system description. This describes all the building systems, structures, components, equipments, including drawings, including some services there, and interdependencies and impacts of on the surrounding facilities. Here you can see the contents that is shown for small facilities, but more or less it's the same. Then also the same chapter, facility description, includes information about radiological status. Based on both operational records, can be also based on the historical site assessment and on the characterization survey. And the facility operating history, featuring information about significant events, some refurbishments, updates, modifications done to that, also occurrences, etc., etc. Strategy selection. Here, also, you remember we have this staged approach to decommissioning plans. So alternatives for strategy to decommission are considered here. Initially, both strategies, and in final decommission plan, normally one strategy is chosen, and all the further information given in the plan, including the actual activities to decommission the facility, they are made with consideration of this chosen strategy, and that also reflects the end state. So what end state should we reach in the end? And to be able to, for example, release of site, or sometimes it's decommissioning without release of site, or sometimes you have multi-facility sites, or there are different options for that based on the specifics of exact site and facility. And the strategy should be justified in this chapter. Project management includes information that will relate to implementation of decommissioning projects, including this reference information on all the applicable legal and regulatory requirements, administrative systems that are to be provided for decommissioning projects, including all schedules, costing, change control, change management, records keeping, etc. And normally the structure is shaped up for the project management organization, like organizational charts with all distributed positions to be filled in. Some personnel might come from operational phase into this phase and perform certain functions. Somebody can be contracted from outside, or some. So it should be clearly stated and visible in the decommissioning plan how this also personnel structure is going to be set for the decommissioning project, and how positions and qualifications will be filled. Then task management, organization and responsibilities. That's also include description of these responsibilities and procedures for the tasks during decommissioning. And other things like safety culture, training programs, requirements and documents and procedures, contractor supports. So some tasks might be delegated to contractors, especially for some complicated or specialized tasks where a lot of training is required, or some specific knowledge and expertise. Can be also subcontracted for supervision of decommissioning and other things. And schedules, so scheduling of the decommissioning project. Also, I reference here that ISSG-49 for small facilities integrated management system is reference. It was not included in ISSR-2025, but I assume that it's also good to have it there as well for all facilities decommissioning. Then this is like the hard, that was soft part. This is hard part of the activities. So this is actual decommissioning activities. are described in this chapter, and here we give the summary of all tasks that are to be performed during decommissioning, and it should be related and describing like all layers containing structures, systems and equipments, soil, surface and groundwater, the buildings themselves, whether they are demolished or not, and all of other aspects up to we reach the end state of the decommissioning. So based on the chosen strategy. This also should describe the chosen techniques, chosen equipment, some measures to protect from radiation and other non-radiological risks and hazards, necessary procedures, and what of that scope would be subcontracted, and what would be performed by the own personnel. Just to mention, it's also really good if if we are still able to keep the personnel that was doing the operational phase, because at least for some works, because this personnel definitely has a lot of knowledge of the facility, all of these small details that contractors might not know, and so sometimes it's good to work to have some option containing both uniting both the personnel from the facility and subcontractors that can do some exact tasks. And schedules for implementation of decommissioning activities is also included here. Also, just in a couple of words, that there are chapters about surveillance and maintenance containing information on the this surveillance and maintenance needed for system structures and components to ensure safety during decommissioning, as well as what equipment and systems would be used for that, and what is the schedule for these types of works. Waste management is covered also still in another section or in a separate document in the waste management plan. So normally, as mentioned here, it's a separate document, but for smaller facilities, it can be incorporated or referenced in the decommissioning plan. So we should have the plan identified all the waste streams for solid, for liquid, or something, or whatever you have, with estimates of volumes and activity of the waste, categories, types, and procedures applicable for that. As well as information about storage and disposal locations, and waste tracking system. Then we have the chapter about cost estimates. So you can use different methodologies to provide these cost estimations. There is the methodology called ISDC. It was developed by OECD, and there is a big document available online. Freely available, so you can check there. There is a structure for this decommissioning costing, and also as an example for smaller facilities. For example, there is for research reactors, there is a cost estimation system that is called SEREX. That's a calculation tool, or not calculation, but estimation tool for research reactors, made in Excel. So it's also possible to use this. You can actually SEREX is also based on ISDC, and the cost estimate is done for the entire project with all this definition of details, tasks, assumptions, resources needed, and how will they be attracted to the project with all sufficient level of detail, and also with the level of uncertainties, and funding mechanism. Then this is in light blue because it's only mentioned in SSG-49 for small facilities, but for bigger ones, you can always refer to GSR Part 3, and these are basic safety standards. They cover radiation protection, but in SSG-49, it's also included in the plan. So of course, this radiation protection plan is also prepared for the decommissioning phase. And safety assessment, normally it's a standalone document, and it can be incorporated as a summary in the decommissioning plan, but also can be fully included, not very big for smaller facilities. So here we evaluate all potential hazards and their consequences, and risk assessment is done for proposed decommissioning activities. Environmental impact assessment also is an important part of the decommissioning plan or separate document, and also it includes the information about and suggested activities to involve stakeholders into this process and to involve regulator. Health and safety plan, both for radiation protection and industrial health and safety. And yes, here it's just a little bit more details on what is included there. So for radiation protection part, nuclear criticality safety, industrial health and safety plan, and some other features such as dose estimations for the decommissioning works, clearance criteria and state criteria. And the quality assurance, so it's quality management aspects of the project. So we also incorporate information about modifications of existing quality assurance program, and here we explain differences that will be done to the quality assurance for decommissioning phase. And the emergency arrangements. So emergency plan is taken from the operational phase, and based on that, the decommissioning emergency plan is updated and performed. Here we can mention that hazards are normally less for the decommissioning phase because we already removed the fuel if fuel is part of a facility, and we gradually reduce other risks and hazards, so it's a little bit less complicated for decommissioning. And security and safeguards. This here it's depending on the type of facility again, whether you talk about spent nuclear fuel, whether it's a part of the facility, or in case of smaller facility, it's just some considerations. But still, for example, for sources like high activity sources, there are some certain aspects to be taken in mind. But here we use a graded approach. And also here, just to mention, because, for example, in decommissioning phase, you might have contractors that are coming to the area, and so the access should be restricted. So all this should be considered, that people will be coming and going. Sometimes it's people from other organizations, so it should all be considered also in this chapter. Final survey is the final document that is prepared based on when the works are completed. We do once again the radiological survey that shows and proves to regulator that we can release the site. If that's reached, if not reached, then we should, as I was showing yesterday the scheme, we should get back to earlier phases and see whether we can do some extra decommissioning works on decontamination or something else, or we can revise the end state, for example. And some other aspects here, as you can see, should be included into the plan. This is just how it works for smaller facilities, how it's included in the decommissioning plan for suggested as an example in ISSG-49. But I will later show the presentation, so you can also have this as a reference. And summary, just to conclude, so once again, that's decommissioning plan is the main safety-related document for the entire decommissioning project, and it ties together all the aspects of decommissioning. It can have one document or document plus numerous appendices and references to other documents, but at least for smaller facilities, it should contain a summary of those documents in it. And the initial plan is prepared early in the design or other early phases of facility lifetime, and it evolves during the operation and then during preparation for decommissioning, and can be updated periodically. It contains large amount of detailed information, and the information, the more detailed, the closer you get to the decommissioning phase. And even then, in the decommissioning phase, the decommissioning plan can be updated when it's necessary, or when it's required by some situations, let's see. Again, all these documents, decommissioning plan and supportive documents, are the main sources of information for regulator, so that regulatory body could make decision on whether the facility can be safely decommissioned, and in the end, whether it can be the site can be safely released from regulatory control. So it's really important to remember and to pay attention and to work on accumulating necessary information and on preparation starting from early phases to have this plan as good as possible for a successful, safe, and efficient decommissioning project. Here are the references that on the documents that I used for this presentation. So again, it's General Safety Requirements Part 6, decommissioning of facilities, SSG-49, decommission of small facilities, because it contains also example of decommissioning plan for small facilities, and this SRS-45 standard formats and content for safety-related decommissioning documents. So thanks a lot. I'm finishing this presentation with the quote from Antoine de Saint-Exupéry from Little Prince, that the goal without a plan is just a wish. So I wish you all, in case that is the case for you, to now be ready to prepare good decommissioning plans. In our trainings, when we at IE have trainings for member states on decommissioning plan, we also normally propose them, suggest them to take the structure of decommissioning plan from SRS-45 and just to try to fill it in with the existing information about your facility, just to see how, like, what information you already have, what is missing, and that helps to then create certain plan for you for the future to steadily come to the phase of decommissioning with expectations, what else do you need to prepare, and that really helps in the implementation phase. Thank you very much.
Thank you, Yulia.
Thank you.
Any questions? I see no raising hands.
But you can have my email just in case you have any questions. You can also contact me by email.
Yeah, thank you. Thank you very much once again. And it was our last lecture, but not the last activities. So thank you, Yulia, again, once again.
Thank you, my pleasure. Bye-bye.
So now just a short presentation about the tests, the initial and the final tests. We'll go through all the questions. And the first part, the first 16 questions were the same in introductory and final tests, so it will be easier to compare how the school was it successful or not. So first questions, just general question about the radioactivity. Very good results already in the beginning. So on the left it is introductory test, and on the right side it is the final test, the results. So almost all of you were correct. And then how activity depends on time, also even a small progress, but it's already a very high percent of the correct answers. Then the unit for measurement in the standard system is becquerel. So again, progress during the school. Radionuclide, that is fissile in thermal nuclear reactors, of course, it is uranium-235. And again, even if it was 96%, now it's 100%. So very good result, I see. Yeah. No, the standard unit, only becquerel. Curie is non-standard unit. It is a derivative from the becquerel, but it's non-standard unit. Yeah, we use it, but it's not standard. Yeah. Mm-hmm. The objective of the decommissioning is to reach the an agreed end state. So again, a lot of correct questions. So it's very good from the very beginning. Responsible for the decommissioning strategy is the facility owner or operator. Here we see quite a huge progress after the school. Incorrect answers. Which decisions concerning decommissioning require stakeholder involvement? Any decommissioning activities. So again, it was a slight distribution of not very correct answers, but again, it was already high percent of the correct answers. The intermediate level waste mobilization. So it's a difficult question. When I wrote this question, I have in mind only cements, because bitumen, they were used previously for intermediate organic level waste. Today they exist, but it's like legacy, and we have to treat this bitumen waste and to place them in another metrics. So for intermediate level waste, mainly it is cement. But today, actually, we see that for some radioactive waste, like spent resins, it may be some polymer matrices as well. So both answers, A and C, may be correct. Okay. So the transition state or period of nuclear facility starts after the final reactor shutdown. Again, quite a big progress after the school. And the question number 10 is not so obvious, because many of you answered that the decontamination is an inevitable part of the decommission, but actually it depends on the balance of safety and cost. Yeah, I showed you this examples as well. So, but again, there is progress in the correct answers, so it's good. Disadvantage of decontamination, of course, the production of the secondary wastes. And again, now it's 100% correct answers. The conditioning of dismantled materials and secondary waste, it is operation to produce the waste package suitable for handling and further operations. So again, quite a lot of correct answers and even progress. What is site remediation? Here it was a bit strange results, because in the beginning it was more correct answers than after the school. I'm not sure why it was so, but we remember that it is to reduce the radiation risk from the contaminated area. So what is the exceptional case? And now we know that it is, of course, in situ decommissioning or entombment. So it's a very exceptional case, very specific. So at which stage one can use conventional technology? Also, after checking the answers, I realized that the question should be more specific, and maybe I should add the word, maybe one can use only conventional technology, so something like this, because the correct answer here was demolition. Sometimes dismantling also can use the conventional technologies. But demolition, it is absolutely sure that at this stage we can use conventional technologies. So again, quite a big progress in the correct answers. So now the part that was not in the first introductory test. Advantages of the cementation are low temperature of the process and the cements, they're acceptable for very wide variety of the types of the radioactive waste. So these both answers are correct. So again, so together it's 85%, so it's good. Which two parameters are mainly considered for classification of radioactive waste? It is half-life and activity content, so quite a lot of correct answers. The first step in treatment, I was really surprised that almost all of you answered correctly, because it's also not very obvious question, but I find it a very good result. Which statement on release criteria is true? Of course, it can be very individual for different countries and different sites, and it depends on the regulator in your country. Also, a lot of correct answers. Who is primarily responsible for managing and implementing the decommissioning project? It is licensee, not the regulator. Regulator can approve the project, but management of the project, it's on licensee. Which methods can be used for separation of radionuclides? Actually, all of them. Yes, so all these answers are correct. So 100% of the correct answers. What are the main characteristics of detector? Of course, most important of them is detection efficiency and resolution, but sometimes we also include the background noise depending on the activity of our objects that we measure. So again, almost all of you answered correctly. What is not one of the safety barriers? And it is, of course, the well for the monitoring of the radionuclides in the environment. Metrics, it is also one of the safety barrier. Will you participate again? So there is no correct, yeah. So it's your choice, but I'm quite happy that 88% of you answered yes. So I find it's a very good result for us. So and now the total result. In the beginning, it was already very high ranking, very high percent of the correct answers. But after the school, we see even good progress. So now it's 80% of the total correct answer. So congratulations for you and for us. And again, thank you for coming. And now, coffee break. Coffee. 10 minutes. Yeah, 10 minutes for tea and coffee and some. When I was like to read it. Yeah. Mm-hmm. So we'll start at 12:15. Yeah, okay.